Dear students, in this video we are going to describe a wave and will derive general formula for the wave. So first of all, we will take our start with the de Broglie hypothesis. De Broglie hypothesis. So now what was the de Broglie hypothesis? De Broglie in 1923 said that with every material particle, with every material body, there is an associated wave. There is an associated wave. And mathematically, the de Broglie wave can be represented by lambda divided by h over p, that is equals to h over mv. So the de Broglie wavelength is equals to h over mv, where h is the Planck constant. So after the de Broglie, that he said the wave, there is the wave related to every material body, and he named it like a matter wave. Matter wave. Now the question is, now what kind of wave is this? So what is the main question here? The main question here comes to be the wave of what? So what kind of this wave is? So as we know that in the case of water wave, let's suppose if we have a water wave, in water wave the in which the quantity that varies periodically is the height of the water from the surface. And let's suppose another example, that is the sound wave. In sound wave, it is the pressure that is the variable quantity. And in light, for example, the light wave, in which we have the changing electric and magnetic field. So here the variable quantity are the electric and magnetic field. So by the variation of which constitute the electromagnetic wave. But what is it that varies in the case of matter wave? So it is this one is the huge question. What is the variable in the case of matter wave? So the quantities whose variation make up the wave is called as wave function. So this is here comes to be a most famous notation, wave function psi. So we can say that the any quantity whose variation, the quantity whose variation make up the matter wave, make up matter wave is called as wave function. So it can be represented by psi. As the psi symbol, psi, which is called as a wave function, it is a Greek word. And now, so here the psi, which represents the wave function, which is the Greek letter. So the value of psi at any point x, y and z in the space at any time t, at any time t. So its value at any point in space x, y, z and at any time t is related to the finding the body there at that time. Okay, this wave function psi itself has no direct physical significance. There is no direct physical significance for the wave functions. So there is a simple reason why psi cannot be interpreted in terms of an experiment. The probability, there is the reason for this one is the probability. So in quantum mechanics, we always talk in terms of probability. So if we say that there is the probability of finding the particle here, that particle is certainly here, then it has the maximum probability, and the maximum probability 1 represents there is the probability is the maximum. And if there is no probability of finding the particle, that means that it will be equals to 0, that is minimum probability that particle, there are the more chances that particle cannot be found here. But an intermediate probability says, we say that the probability is 0.2, means that there are the 20% chances. There are the 20% chances for the particle being there, for an object being there. But the amplitude of any wave is a negative as often it is the positive. And negative probability, for example, we say that minus 0.2. Minus 0.2 probability, it has no physical meanings. There is no mean of saying that there is minus 0.2% probability of finding the body. So minus 2 is the meaningless. So psi, we can say that psi itself has no physical significance. Instead, we take psi amplitude square. Psi amplitude square is always comes out to be the positive, and psi amplitude square is called as probability density. It is called as probability density. So it's always comes out to be the positive. So absolute value of the wave function, which is known as probability density. So probability of experimentally finding the body described by a wave function at the point x, y, z and t, which is proportional to psi amplitude square at time t. So whenever the psi amplitude square has its value is maximum, it has the large value, then large value of psi square means that there is the strong probability of finding the object there at time t. If the psi amplitude square has a small value, and small value correspond to having there is the slight probability or less probability of finding the object being there. So this probability, this definition of wave function or this interpretation of wave function was first time given by Max Born. Although this wave function psi was invented by the Schrödinger, but at that time he was unable to describe the wave function. Later on, it was a Max Born who interpreted the wave function in terms of probability density, and he said that wave function actually encodes the probability. Probability means it's encodes all the possibilities within it. Now we are going to describe the wave. We will describe a general formula for the wave. So a general formula for the wave. General formula for wave. So the general formula for the wave can be find out, but before this, here we will impose another important question, that is how fast de Broglie waves do de Broglie wave travel. De Broglie wave travel. So it is an important question which need to be answered. So since we associate a de Broglie wave with moving body, and we expect that this wave has should have the same speed or same velocity as that of the body. So let us see if it is true. And if we call the de Broglie velocity as a Vp, so here we represent the Vp, which is known as de Broglie wave velocity, de Broglie wave velocity, and is equals to mu lambda. And so lambda is the wavelength, which is de Broglie wavelength, and we know that lambda is equals to h over mv, h over alternatively it can be equals to h over p. So to find out the frequency mu, we need to equate the expression for the energy. We have two equations: E is equals to h mu and E is equals to mc square. So relativistic formula for the total energy. We can equate both these equations, and we can write it like h mu is equals to mc square, and here the mu will be equals to mc square divided by h. So here now we have the value of mu frequency, and we also have the value of wavelength, which is lambda is equals to h over mu. So we can put these value into this equation. This implies that de Broglie wave velocity is equals to mu lambda. It will be equals to, by putting the value of mu, mc square over h into h over mv. So here the Vp, that is the de Broglie phase velocity, comes out to be equals to c square over mu. So it is the de Broglie wave velocity. So it tells us that the particle velocity v must be the less than the velocity of light c, but here you can see that the de Broglie wave always travel faster than the speed of light. So this is an unexpected result, and in order to understand this result, we must know the distinction between the phase velocity and group velocity. So in order to answer to this question or this unexpected results, in our coming video we will discuss its reason, and then by and distinction between the phase velocity and group velocity. However, here now we come to our topic, that how we can derive a general formula for the wave. Here for simplicity we consider a stretched string, and along the x-axis it's like this one. So this one is the x-axis and this one is the y-axis. So here we take the plus a, 0, and minus a. This one is the x-axis. So this is the vibrating string, and here we have a wave, and so this is the vibrating string. At this one is for at t is equals to 0. Let's we take another one at x is equal to 0. That is, again, this one is the y, a, minus a, and 0. So again we have like this one. X is equals to 0. This one is the x-axis. So here you can see that string is vibrating along x-axis, both figures, and it has its motion along the y-axis, vibrating along the y-axis. And here you can see that it's at time t is equals to 0, it has the maximum at x is equals to 0. So at time t is equal to 0, it has maximum at x is equal to 0. So its displacement at any future time t at the same place, that is at x is equal to 0, can be given by a formula y is equals to a cos of 2 pi mu t. Here a is the amplitude, here is the amplitude of the wave, that is the maximum displacement from the mean position, and here you can see that maximum displacement at t is equals to 0 is correspond to at x is equals to 0 we have the maximum displacement about the mean position, that is this one is the central position is the mean position. So here is the maximum displacement at x is equal to 0 which correspond to at t is equal to 0. So at any future time t, the displacement at the same point at x is equal to 0 can be represented by y is equals to a cos of 2 pi mu t. But here the problem with this formula is that this formula tells us or describe that the displacement of the single point. It describes the displacement of single point on the x-axis and with some frequency mu, and it tells us that displacement of a single point on a string at time t. So it only describes at point x is equal to 0 at time t. But the complete description of the wave, a complete description of this displacement requires that we should know the value of v at any point and at any time, at any point along x-axis and at any time t. So what we need to do and what we want to do is that to form a formula giving the y as a function of x and t, not a function of only t or the function of x. It should be function of x and t simultaneously. That's why then we can find the displacement at any time t and at any point along the x-axis. So let's suppose so here take another figure like this one. So here again we have a stretched string at along the x-axis at t is equals to 0. Okay, here we have a hand, and with the help of hand we shake the string. When we shake the string, it will produce a wave, and these waves are like this one. So these waves which produce as a result of shaking, and these waves travel down along the x-axis, and at time is equals to t it reach at point x. So this one is the y-axis, and here we have the periodic motion along the mean position, and so during this time the distance covered by the wave is equals to x is equals to vp into t, and the time taken by the wave to reach at point t will be equals to t is equals to x over vp. So here is the one thing to note is that as the wave travel along x-axis and it reach at this point, and distance covered is x is equals to vp into t. Here vp is the de Broglie wave velocity, and time taken during this distance is x over vp. Hence we can say that displacement y, this one is the displacement y of the string at any point along the x-axis is x over is the same at as it is at x is equals to 0. As here we can see that at x is equals to 0, this one is the displacement, and again if we say at this point, again displacement is the same. So at any point it has the same displacement, same value of the y at x as it has at x is equals to 0 at some earlier time. So here the earlier time can be equals to t minus x over vp. So earlier time is t is equal to x over t minus x over vp. As we have calculated the formula for the wave of a single particle is equals to a cos of 2 pi mu t. Now putting the value of the t, we will get the formula can be modified like a cos of 2 pi mu into value of t will be t minus x over vp. So this is one is called as the wave formula, general wave formula, and now we can further modify it. Now how we can modify the wave formula? So we can simplify it and we can write it like y is equals to a cos of 2 pi and mu t minus mu x divided by vp. And so as we know that vp is equals to mu lambda, and so by putting this value the y will be equals to a cos of 2 pi into mu t minus mu x over mu lambda, and it will be equals to y is equals to a cos of 2 pi mu t minus x over lambda. Now we have some other important quantity related to the wave, and these are the angular frequency, and which is can be represented by omega is equals to 2 pi mu, and another important parameter is the number. Wave number is can be represented by k is equals to 2 pi over lambda, and when we multiply and divide by the mu, 2 pi mu over mu lambda, then k will be equals to omega over vp. So the unit of omega can be measured in the unit of radian per second, and k wave vector or wave number has the unit of radian per meter. So we can write the wave equation again in terms of omega and k. So as again we comes to the wave equation, as we know that the wave equation is y is equals to a cos of 2 pi mu into t minus x over vp. So we can write it like y is equals to a cos of 2 pi mu t minus 2 pi mu x over vp. So it can be written as like this one. So it will be equals to y is equals to a cos of 2 pi mu is equals to omega t minus again 2 pi mu is equals to omega, and we have x over vp. And again it can be written as y is equals to a cos of omega t minus, here I can write it, this one is the value which is equals to omega over vp is equals to kx, as omega over vp is equals to k and we have x. So this is our wave formula in term of angular frequency and wave number. So we have the wave formula in term of wavelength and frequency, and in term of angular frequency and wave number. In although in the three-dimensional wave we can, again this is the wave formula for one dimension, and for three dimension again we can write it like y is equals to a cos of omega t minus k dot r. So here instead of x we can write the dot product of k dot r. So this was our general formula for the wave function, for wave formula, and which describe the wave. Thanks for watching. For more videos please subscribe our channel.